This video is about free fall and the acceleration due to gravity. You have learned that acceleration is the rate of change in speed or velocity divided by time. You can see the equation here. Acceleration equals a change in velocity, so it would be final velocity minus initial velocity divided by time, the time that it takes to make that velocity change. Now, all accelerations are caused by forces. That's Newton's second law, that the acceleration of an object will be proportional to the force applied to it and inversely proportional to the object's mass. One force that we have to consider in a number of different situations is the force of gravity. Gravity is a force, and therefore it can cause objects to accelerate. In particular, gravity accelerates falling objects. This acceleration due to gravity is the subject of our lesson. You may have heard of a famous experiment involving gravity. Galileo proposed if you drop two objects from a height, such as the Leaning Tower of Pisa, that you will observe them hit the ground at virtually the same time. Maybe not exactly the same, but it will be very, very close. Galileo may not have actually carried out this experiment, but many other people have, and they've found exactly what Galileo predicted. One reason this experiment is so famous is the results are counterintuitive. If you imagine a very heavy object, say a 10-kilogram cannonball, and a lighter object such as a 1-kilogram musket ball or a stone, and if you drop them both at the same time from the same height, it just seems logical that the larger object would fall faster and therefore would reach the ground first. It does, in fact, reach the ground first, but only by a minuscule, tiny fraction of a second. Now, it's important to understand the implications both of the real results and Galileo's prediction. Galileo said that regardless of what the object is, it should accelerate at the same rate. The only reason that we don't observe them hit at exactly the same time is because of air resistance. So when there is air resistance, the larger object may in fact go a little faster. It might actually go a little slower. It really just depends on the shape of the objects and some other factors that we're not going to go into right now. How can this be possible? How could two objects which have such an obvious difference in weight and therefore such an obvious difference in the force pulling on them, how could they fall at approximately the same rate? Well, Galileo pointed out that even though the force acting on the more massive object is greater, it does have more mass. And those two quantities are proportional. The 10-kilogram cannonball, for example, would experience 10 times as much gravitational force as a 1-kilogram stone. In other words, the 10-kilogram cannonball does weigh 10 times as much as the 1-kilogram stone, but Newton's second law, which Galileo actually was the one that came up with this, says that force equals mass times acceleration. If the acceleration, in this case, is due to the acceleration of gravity, then if m goes up, F goes up by the same factor. In other words, if the mass gets larger, the weight gets larger. Weight is represented in these fractions with an F, and it shows you the ratio of force to mass. But the ratio of force to mass is acceleration. That's Newton's second law. A equals F over m. So if F and m both go up by the same factor, that means A stays the same. In other words, all freely falling objects undergo the same acceleration at the same place on Earth. When one object is more massive than another, it does weigh more, it does experience more force pulling it towards the ground, but the ratio of force to mass is a constant. Here's another way to think about it. Mass is a measure of inertia. Mass is a measure of how much stuff is in an object, and the more stuff, the more that object resists changes to its motion. So if mass goes up, resistance to change in motion, in other words, resistance to acceleration, increases. So if you have 10 times as much force pulling on something, but it has 10 times as much resistance to that force, then that ratio produces the same acceleration. Larger objects do weigh more and get pulled harder towards the ground, but they resist that pull. They resist the acceleration 10 times as much as well. So no matter what the object, the ratio of weight or force of gravity to mass is the same if air resistance is neglected. In real life, of course, you can't neglect that, but we have to assume perfect conditions for a lot of problems in our class. So, because this acceleration due to gravity is a constant, it's always the same for every object on the Earth, it's given its own symbol, G. Instead of an A, we will often write the symbol G when the acceleration is due to gravity. So shown here is a large object and a smaller one. The ratio of force to mass is the same, and instead of setting it equal to A, we set it equal to G. G is an acceleration. It is an A. It's just a special case of A. It's the acceleration due to gravity. All freely falling objects fall at the same acceleration due to gravity if you ignore air resistance. We're going to talk about that more and more, but this is the ideal situation. If an object falls, it falls at a constant acceleration due to gravity. Here it is mathematically in equation form. The weight of a 1 kilogram stone in the metric system would be 9.8 newtons. So a force to mass ratio would be 9.8 newtons to 1 kilogram. That would result in a 9.8 meter per second squared acceleration. That value, 9.8 meters per second, is the acceleration due to gravity constant. It's represented by a G. Anytime you see G, you write 9.8 meters per second squared. If you have a larger weight, such as a 10 kilogram cannonball, that would be 98 newtons, but the ratio would be the same. 98 kilogram meter per second squared divided by 10 kilogram equals 9.8 meters per second squared, or G. So when a larger object falls, it does get pulled harder. Gravity does have a larger force on it. But because of its larger mass, the ratio of force to mass, which is your acceleration calculation, gives you the same result, assuming there is no air resistance acting on the object. All freely falling objects fall with the same acceleration because the net force on an object is only its weight, and the ratio of weight to mass, which is Newton's second law is the same for all objects. Again, there is a catch. While g is 9.8 meters per second squared for the Earth, it changes depending on where you are, real objects here on the real Earth fall at a little less than g at any given moment due to air resistance, an opposing force. And that is the lesson that you should watch next.